So up to this point, we've talked a lot about polynomial functions. We've talked about how to do division on polynomial functions. We've talked about the zeros of a polynomial function and the intercepts. Now, how do we actually find those zeros? That's what we're going to tackle today. And so today our topic is real zeros, real meaning not imaginary zeros, but all real numbers that we can actually plot and we can actually graph these polynomial functions with these zeros. So let's first start by talking about rational zeros. So rational zeros, we're talking about zeros that can be expressed as a ratio of two numbers. So not all real numbers will be rational, but all rational zeros are real zeros. So to talk about rational zeros, we first have to know the relationship between all the rational zeros and the polynomial function. And so what this says is, if p of x is a polynomial with integer coefficients, and if p over q, written in lowest terms, is a zero of p of x, then p is a factor of the constant term of p of x, and q is a factor of the leading coefficient of p of x. So in this case, we have written ax to the nth power, there might be things in between, and then you have a constant at the end. And so what this is saying is all the rational zeros will be some ratio of a factor of b divided by a factor of a. And so this p over q, you need to understand what they represent. So p is a factor of b, q is a factor of a. So p is a factor of the constant, q is a factor of the leading coefficient. And so all your rational zeros can be expressed as that ratio of p over q. Now, not all the different combinations of p over q are going to be zeros of the polynomial, but all the ones that are zeros will be within that list. So to find all possible rational zeros, you will find all possible combinations of p over q. Let's take a look at an example. So if you are asked to find all possible rational zeros of this function, and then it says to find the rational zeros. So notice the difference. One is all the possible ones, and then one is what are the rational zeros. So we're going to start by coming up with all the possibilities. That means we want to look at the constant term, which is 6, and the leading coefficient, which is 2. So this p over q, remember, p is going to be a factor of the constant term 6, so plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Those are all factors of 6. And then q is going to be a factor of the leading coefficient 2, so that would be plus or minus 1 and plus or minus 2. Now that you have those two lists, you have to come up with all the different possible combinations you can come up with for p over q. So that would be plus or minus 1 over plus or minus 1, plus or minus 2 over plus or minus 1, plus or minus 3 over plus or minus 1, plus or minus 6 over plus or minus 1, and then do the same thing but over 2. So plus or minus 1 over plus or minus 2, plus or minus 2 over plus or minus 2, plus or minus 3 over plus or minus 2, plus or minus 6 over plus or minus 2. So those are all the different possible combinations we can come up with. Now, we're going to take out any, what I'm going to call duplicates. If you look at this, plus or minus 1 over plus or minus 1 is essentially the same as plus or minus 2 over plus or minus 2, right? Once you divide, it just becomes plus or minus 1. So I'm going to go through and simplify each of them, and if there are any duplicates, take them out. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 1/2, and then we have a repeat here, that's also plus or minus 1. We have plus or minus 3/2, and then we have another repeat here with plus or minus 3. So this list here, this is the list of all possible rational zeros. Now that's not to say that these are all actually zeros of this polynomial, but all the rational zeros of the polynomial are going to be somewhere on this list. So how do we know which ones are actually going to be zeros? Well, you take that list and you can use the factor and remainder theorems here. And by plugging each of these in for x in the polynomial, whichever one gives you 0 means the remainder is 0, which then means it is a factor. So to find out which of these are actually zeros, you'll plug them into f of x. Now you can go about doing this by simply doing the whole process of plugging in, okay, let's plug 1 in. So 2 times 1 to the 4th plus 1 cubed minus 17 times 1 squared minus 4 times 1 plus 6, and that gives you negative 12. And so on, but there are going to be a lot of these. So instead of having to do that out every single time, there is a way to have the calculator do this work for you. So I'm going to show you how to do that. Alright, so in the calculator, into the y equals, I am going to go ahead and put in my function. Now that I've entered in the function, I need to somehow find a way to be able to plug in these values of x. Now, on this calculator, you have what's called a table. And so you can go to the table and take a look and see what you have there. So what I have here is I have the table actually already auto fill in all these values, starting with 0 and going up. But these are not necessarily the values that I want. Some of them might be, but I want to be able to input my own value of x. So what we're going to need to do is we are going to need to set up the table so it does not automatically fill in the x values. We're going to go to table set, so that's second window. And then if you see down here, we have independent and dependent. And what I want to do is I want to change, so the independent variable, the x variable, is on ask. That way I can tell the calculator what the x value is. Now I want to keep dependent, the dependent variable, the y value, to be auto. So that way it will automatically tell me what the y value is when I tell it what the x value is. Now let's go back to the table. And now you can see the table is blank now. So now I can plug in values for x and get values of y. And we see here at negative 3 we get y equals 0. So that's going to be one of our zeros, and we'll continue. It looks like 1/2 is also going to be a 0 as well. And it looks like those are the only two, at negative 3 and at 1/2. So that's it for example 1. So we found the list of all the possible rational zeros, that's the plus or minus 1, 2, 3, 6, 1/2, 3/2. And then in order to figure out which of them are actually zeros, we have to plug them in and see which ones give us 0. That means it has a remainder of 0, which means it is going to be a factor. So to find all zeros, you are going to find all the rational zeros, so all the possibilities. And then once you find all of the actual zeros, then you are going to perform synthetic division with those zeros. Once you find that, you are going to take whatever quotient you have remaining and find any remaining zeros there may be. So it might require you using the quadratic formula. Alright, so example 2. Find all the real zeros of the function given in example 1. So we already found that negative 3 and 1/2 were rational zeros. So that takes care of step 1. Step 2 is to perform synthetic division using those rational zeros. So it doesn't matter which one you use first, it's up to you. Either way, once you've done division with both of them, you will end up with the same answer. Let's say we start with negative 3. We do synthetic division. We know that at the end our remainder should be 0 because we know this is a rational zero. So that's a good way to check to make sure you're doing the synthetic division correctly. So bring down the 2, we have -6, -5, times -3 is 15. That's -2 times -3 is 6. And those we get 2 times -3 is -6. And that we get 0. As expected, our remainder is 0. And now we're going to do synthetic division again. Now just so that we know what we have here, we divided by x plus 3. And we were left with 2x cubed minus 5x squared minus 2x plus 2. So we divided by x plus 3, right? Dividing by that -3 means x plus 3. And our quotient was 2x cubed minus 5x squared minus 2x plus 2. So this is factoring out the x plus 3, and that's what we have. Now we want to continue, and we want to factor out the 1/2. So we do synthetic division again. And this time, instead of using the original equation, we want to use what's remaining. So the 2, -5, -2, and 2. So now we'll do the synthetic division again. Bring the 2 down, times 1/2 is 1. And those we get -4. Multiply by 1/2, that's -2. And that we get -4. Multiply there, we get -2. And that leaves us with a remainder of 0. So now again, let's write out what we have. We divided by x plus 3. We divided by x minus 1/2. And then we were left with 2x squared minus 4x minus 4. So this is what we have up to this point. Now, in order to figure out the remaining zeros, now notice this was a degree 4 polynomial, so there should be 4 zeros, and right now we've only found 2 of them. So this synthetic division is to help us get it down to just the quadratic, 2x squared minus 4x minus 4, and then we'll use that and use the quadratic formula to find the remaining zeros. So your a value is 2, your b value is -4, and your c value is -4. So with the quadratic formula, that gives us 2 plus or minus the square root of 12 over 2, which is 2 plus or minus 2 root 3 over 2, and dividing that we get 1 plus or minus root 3. So f of x has 4 real zeros, 2 rational ones that we already found, -3 and 1/2, and it also has 2 irrational zeros, right? So irrational meaning that they cannot be written as a ratio of 2 integers. So that's 1 plus or minus root 3. So we found all 4 zeros, -3, 1/2, 1 plus root 3, and 1 minus root 3. One last example. Factor f of x equals 2x to the 5th minus 10x to the 4th plus 7x cubed plus 13x squared plus 3x plus 9 completely. So the way we're going to factor this completely is we are going to go about the same process, writing out the rational zeros, figuring out which ones are actually rational zeros, using synthetic division, dividing out what we can and seeing what we have left, and seeing if there's any way for us to factor it any further. So let's start with the rational zeros, p over q. So p being a factor of the constant term, which is 9, so plus or minus 1, plus or minus 3, plus or minus 9. And then q being a factor of the leading coefficient, which is 2, so plus or minus 1, plus or minus 2. So come up with all the different combinations, plus or minus 1 over 1, plus or minus 3 over plus or minus 1, plus or minus 9 over plus or minus 1, and put them all over 2. So plus or minus 1 over plus or minus 2, plus or minus 3 over plus or minus 2, and plus or minus 9 over plus or minus 2. Now, taking all of these possibilities, we have to plug them into f of x and determine which ones are going to give us 0. So just for practice, I'm going to go ahead and use the calculator and use that to help me figure out which ones give us 0. So from here it seems that we only have two rational zeros, one at -1 and one at 3. Now that we found our rational zeros, our next step is to use synthetic division to factor that out and see what else we can factor. So start with -1. Again, it doesn't matter which one you start with. In the end, you will end up with the same quotient after you've done the division twice. Bring down the 2, multiply by -1, add those, multiply by -1, add those, we get 19, multiply, we get -19, and add, we get -6, times -1 is +6, and that we get 9, multiply, we get -9, and that we get 0. And again, we should be expecting our remainder to be 0 because we know that -1 is a rational zero. So up to this point, we have x plus 1 times 2x to the 4th minus 12x cubed plus 19x squared minus 6x plus 9. Now we're going to take our quotient from this, and we are going to do synthetic division with the 3. Bring the 2 down, multiply that by 3, we get 6. Add that, we get -6 times 3 is -18. Add that, we get 1 times 3, we get 3. Add that, we get -3 times 3, we get -9, and that we get 0. And again, we should be expecting our remainder to equal 0. So now we factored out x plus 1, we factored out x minus 3, and we're left with 2x cubed minus 6x squared plus x minus 3. Now the question is, can we factor this any further? So take that 2x cubed minus 6x squared plus x minus 3. Are there any other ways that we can factor this? In fact, factoring by grouping is one way we can go about factoring this further. So we can factor out a 2x squared from the first two terms and factor out a 1 from the last two terms. That leaves us with an x minus 3 and a 2x squared plus 1. So completely factored as much as we could, this is x plus 1, x minus 3, and 2x squared plus 1.